Okay, so today we're going to finish up P1. We're going to talk about points of intersection. Points of intersection are where two equations meet. Yes? And that's a solution. You can look at a graph, and then with our calculators, we know how we could it in the calculate. It tells you intersections, or algebraically, you just set them equal to each other, and you're good, right? Am I good to go yet? Mm-hmm. Okay. Okay, so find all the points of intersection of the graph. So on this graph, it's pretty easy to see where they are. Where are they? 2, 1, and negative 2. Okay. So these are the two equations. I said set them equal to each other. Can I set these two equations equal to each other the way they are right now?
No.
No. I have to solve them for a variable. Probably for y. Yes?
No.
So if I solve it for y, I would have x. Ooh.
Why is that so thick? X?
Because I have it on the marker, not the pen.
How dare you?
So I'd have x squared minus 3 equaled y. And I would have x minus 1 equaled y. And now I would set these two equal to each other and set it equal to 0 since it's quadratic. So I would have x squared minus x minus 2 equals 0. Factors of 2 that have a difference of 1. Negative 2 and 1. So x equals negative 1 and 2. I have an x. How do I get a y?
Plug in 0.
Not 0.
Negative.
Negative 1, 2.
Oh.
Okay, so I'm going to plug it in here. How about you guys? Actually, no, I'm going to plug it right here. Because it's already set equal to y. So negative 1 and negative 1 is negative 2. And 2 minus 1 is 1. And is that what they showed us on the graph? Yes. I prefer algebraically just because I just do it and I don't have to worry about it. But with your graphic calculators, it would find these points of intersection. Remember a second trace? It says calculate and it says intersection. So it'd say first curve and you make sure it's on this curve and it would show the equation up in the corner. And you hit enter and it goes to the second one. And then you move your cursor to where close and you say guess. And it would tell you 2, 1.
Yes.
Okay. And the video, no one saw any of that, so we're all good. Am I good, Ainsley? Cadence? Was that a yes?
Yes.
It was a Okay, they just did it.
Don't hit me, Riley.
Okay. Mathematical models. I don't know how much you want to write down of this. A mathematical model is a real life situation. It's a real life application of what you're doing. Okay? So, in developing mathematical models to respect of actual data, you strive for two often conflicting goals: accuracy and simplicity. To get accurate, it is not always simplistic. I had a class in college, it was called mathematical modeling. You think we all went in there just raring to go, right? Because what is the thing we hate the most?
Math.
Application problems. Application problems. And all we did was he gave us a scenario and we had to make a model. We had to go in and use.
Miss Mick, but you're already a model.
Oh, I know.
Like what scenario?
Like one of our big projects, like he would give us a model and we'd have to come up with an equation. He'd give us an equation. We have to get him a model. But one of our big one, we had everyone had different things. But my group had the wolf population in Yellowstone versus the rabbit population in Yellowstone. So when the rabbit population went down, the wolf population was like, as the rabbit's population went down, the wolf population was going up. Why?
Because they were eating the rabbits.
They were eating the rabbits. So then we had a spike at the wolf population and a minimum at the rabbit population. So when there's not enough food, what happens has to happen to the wolf population?
It goes down.
It has to go down, and so then the rabbit population will start going up. Okay, now wolves eat other things besides rabbits, but do they have a direct correlation? That's what we had to see. So we had data on the wolf population, we had data on the rabbit population, we had to graph it, we had to make equations, and then we had to see if they were affecting each other. So it was a huge project. But if I was a ranger at Yellowstone National Park, would that be important information to me?
Yes.
Yes. So mathematic models are real life. Like, they're used all the time. Anybody who has to make a prediction has a mathematical model. And someone has to be smart enough to make that model.
So who dressed up as the wolf?
No one. Okay, so we have carbon monoxide in parts per million on the Earth's atmosphere. The January readings of various years are shown. Okay. So, what is the difference between the two models?
That one has
Left or right?
Right.
Okay, on the right one.
Thicker, like line going up.
But don't they
all
have
the way
the
up
same? Okay, they're recording it in Hawaii. So why do we have two graphs?
Because that line on the left stops like halfway up, like being thick, and then the one on the right is like thick all the way up till about a little bit over 400.
Yeah, but I get that. I'm asking why there's two models.
I don't know.
Because we have years on the bottom, right?
Yeah. Maybe it's.
And then we have parts per million in CO2 on the dependent axis. Are all our numbers the same?
Maybe they're different years.
Well, the years are on the bottom.
There are years on the right one.
So 1910, 1920, 1930, 1940, 1950, 60.
Yeah, I was gonna say that too until I read that.
And it's the same. So I was thinking it was the same data with a different scale. You know what I mean? Like, I thought the left was,
But they're the same.
but they're the same scale. That doesn't make sense to me. That is really weird. Okay, at 30 years, we're like 350, right? 30, we're like at 350. Did they just blow it up? No.
Yes.
No. And then I thought it was at two different places, but is it at two different places?
No.
No. It just says Hawaii.
I'm confused.
Observatory in Hawaii records the carbon monoxide concentration in parts per million in the Earth's atmosphere. The January readings of various years are shown. Huh. Let's do the next one. Maybe they just weren't supposed to give us the other one. Okay, we went back to this one. Okay, so somebody took the time and found the equation that to give me this. And honestly, guys, what you do when you have that is you plot your data, you plot the points, and then this would be quadratic to me. If I had the other side, wouldn't it? To you? Is it a quadratic shape?
Yeah.
Okay. The other choice would be exponential, but wouldn't exponential like shoot, like, let me try here. So if I'm looking at this data, I know I don't need past 0 years. That doesn't make sense. But if I mirrored it, it would be more like a quadratic because an exponential would do that, wouldn't it? So you start with a quadratic, and then you start with, okay, well, my y-intercept is 316.7 because I would have the actual data, right? Mm-hmm. So that's where this 316.7 comes from. And then you start messing with these numbers.
Well, how'd they get those numbers?
They just start messing with them.
Find it, like,
You start with t squared plus t plus 316.7. And then you start changing those numbers. And you're going to keep graphing this line, and you're going to do that until that line fits it. Now, there is a mathematical process with statistics that gives you a little bit better way to do it, but I'm saying that's what could be done. You find a shape, and then you start doing it. Well, when I put it if I had it on a graph, if I put the 1, it would be like down here, like it wouldn't fit it. It would come up like this. So I need to lower it down. So you start messing with both of those numbers. Okay? It's just a million slides to tell me nothing.
That's how I'm feeling right now. I haven't written down nothing.
Okay, now wait a second. This what tells me B did. B represents the years 1960 to 2020.
So the second graph.
So the second graph, so let's go back. They should have done that over here. They should have put that down here, shouldn't they?
Yeah.
So this was 1960
To 2020.
to 2020. Because at first I just thought they zoomed in,
Yeah.
but they didn't. So 0 was 1960, so this is 1970.
They really messed up these pictures.
Yeah. So the carbon dioxide concentration is going up, isn't it?
Yeah. Isn't it?
Not as fast. I don't know. Without the actual data, it's kind of hard. Okay, so what was the prediction given in the first model for 1960 through 1990? Those were just predictions. So you'd look at the model and you'd go, I love how we don't have this. Okay, so 1990 would be where? 70, 80, 90?
30.
So what do you think our prediction is? 250?
350.
350? Okay, so there's our prediction if I just use the model. This was a prediction model. The other one was an actual model. Okay, so now if I plug in that many years, which is 75 years, no, it wouldn't have been 75 years.
You're plugging in T for time.
Oh, this was just, yeah, I know. This was just a prediction. That was just a prediction. Given the second model for 1960 through 2000, does the prediction of 2035 seem accurate?
Yep.
So if you 2035 would be 75 years, yes. And so we got 350 off the chart for 220, right? Or 1990, sorry, not 20. And if we plug in 75, does 480.2 parts per million seem reasonable?
I guess.
Yeah. It's not outrageous, right? It's not like it went 900. If they said 900, would we probably be like, Why do you think it's going to slow down? Because to me, that rate's slowing down some. Are we more conscious about our pollution and all that kind of stuff? Well, we're more knowledgeable of it. Whether we're conscious of doing anything about it is another story. But we are there's more regulations and stuff, right? So, mathematic models, you just have to. Oh, this is just a concept check. So we're done. Mathematic models are just there to represent what we see in real life and interpreting that. So when you guys are going through those problems, it will be multiple steps. You will pull out a calculator and do some stuff. Dig into it, okay? Think. I'm not going to give you 18 of them, but when I give them to you, go through the motions and use the calculus to find what you're doing, okay? That's it. That's all I have.